Hello all. So this one is the lecture on the inverter gate. But before we start talking about the inverter gate, we need to talk about the type of signals that we're going to deal with in this class. So last time we learned that signals come in two flavors, analog and digital, and we're going to talk about digital signals. Well, our digital signals are going to be very, very easy. You're going to have a digital signal of 1, and that corresponds to high voltage. And that is voltage anywhere from 2 volts all the way to about 5 volts. And then we're going to have low, and that's a 0. And that would be low voltage less than 0.8 volts. So this is a very digital signal. You have either high or you have low. You have 1 or you have 0. You have true or you have false. And you shouldn't have anything in between. Okay? But we do have an in between right off the bat. You can see that you have a very interesting region in between 0.8 and this is going to be undefined all the way to 2 volts. That's an undefined region, and it's neither high nor low. It's something in between. And I just told you that we're not going to have that, and that's because we're trying to impose a digital signal on the very analog world. Our signals are going to be always voltage. And voltage signals in general, you can encode music in voltage signals, and that will be an analog recording. That's absolutely possible. But we are not doing it like that. So we're just gonna digitize that signal. So this means that this undefined region we have to avoid, because that will completely mess up our circuit. So now let's talk about the inverter gate itself. I think of an inverter gate as a recipe or a blender, if you will. If you have a blender, you throw in some strawberries, you throw in some bananas, and you hit a button and out comes a smoothie. Well, logic gates in general are just like that. You send in a signal, something happens to it, and out comes a changed signal, a different one. The one that no longer looks like the signal that you put in. So this is the symbol for the inverter gate. It has this little nice triangle, and it also has a very nice circle on the nose. And you have a signal coming in over here on the side. This is going to be V in. And on this side, you're going to have a signal coming out, V out. So let's see what happens to the signal inside the inverter gate. So I'm going to draw this little table. We're going to put in so first, I have only 2 options to send. 1 or 0, right? So first I'm going to send in 1. And what comes out of the inverter gate is a 0. And then I'm going to go ahead and send a 0. And what comes out is a 1. So the signal is inverted. Every single time you send a signal, you get back the exact opposite. And that's really all there is to know about the inverter gate. It really is that simple. So next thing we're going to do, we're going to apply that inverter gate to a circuit. And our circuit is going to be a tripwire. So in order to do a tripwire, I'm going to use software called Multisim. This is what it looks like. And before I'm going to go on and build a circuit using inverter gate, I'm just going to build a very regular circuit so that you can see how we can change that to turn this into a tripwire. So first I'm going to place a battery, and it's DC power, battery pack, and the ground. This particular software always gets very upset if you don't place the ground. It's not going to work. I'm going to change the battery value to 4.5 volts. I'm going to connect them up. So I'm going to build a very basic circuit. I'm going to build a circuit with an LED light. I'm going to use a red, and resistor, and a switch. And at some point I will make a multi-sim introduction video for those of you who missed that lecture, so that you know how to use multi-sim. Multi-sim is not going to be on your final for the fall semester, so that's not a very pressing concern for me right now. Okay, so here's my circuit, and in multi-sim you can simulate the current flowing. So when I hit the play button over here, I'm going to start the simulation. You can see that my switch is open and my LED is off. My switch is closed, my LED is on. Well, in my tripwire, I want to have the exact opposite thing. Every single time I open the switch, I want my LED light to come up to signify that the tripwire is broken. Because when you think about a tripwire, it's just a wire. This is your tripwire. And how do you trigger a tripwire? You break it. And the broken wire looks exactly like this type of switch. Alright, so I was just talking about this inverter gate, right? And it does exactly that. It inverts the signal. So it would seem that if I put an inverter gate over here, then every single time it gets a high, and 4.5 volts is a high, right? Because it's in between 2 volts and 5 volts. It will give out a 0. So my LED will turn dark. And then every single time my switch is not closed, it's going to give me a low, and my LED will turn on. So the component I'm going to place, the inverter gate I'm going to place, is the same type of inverter gate we're going to physically use in class, because this is a simulation and you can simulate the actual behavior of an actual logic gate that exists in real life. So this is where I'm going to get it. It's in TTL, that's right here. And then I'm going to go into the family 74S, and it's 74SO4M. So I'm going to place it right here, and it immediately tries to place another one, so I say no. And now I'm going to run my simulation. Oh, awesome. So my LED light, my switch is closed, my inverter gate gets a high signal, it immediately inverts it into a 0. Well, 0 volts is definitely not going to light up our LED, so it's dark. So now when I'm going to open my switch, it should turn on. Uh-oh. Looks like that doesn't work. I wonder why. Well, guys, if you look at the very beginning of what I told you, we have to give it a high or a low. And the thing with this circuit, we're giving it a high when it's closed. But when we open the circuit, we are not giving it anything. It could be low, It could be high or it could be undefined. We're literally not telling it what we're giving it. Okay, well, the question is, do I actually have a low in my circuit? And yes, I do. That's the ground. The ground, guys, by definition is 0 volts. So I'm going to make it black. So everything that's colored in black right now, well, this one should go also black. But now everything that's black is 0 volts. Well, that sounds really good. That's way less than 0.8. So that should give me a nice 0. So my next idea would be to place a little wire over here. So now when my switch is open, I have 0 volts. And when my switch is closed, I have 4.5 volts. So when it's open, I have a low. When it's closed, I have a high. So let's test this out and see if this works. Oh, it's open and I have a high. And my light is on. Awesome. And then I close it and it's still on. What's going on? Okay, guys, notice that when I close this, I have a very, very, very bad situation in terms of my circuit over here. So this is what happens. Think about electrons. An electron comes out of your battery and it comes to a fork in the road. On one side, it can do a lot of work. It would have to go through an inverter. It would have to go through a resistor. That's a lot of work. And then it will have to light up an LED. That's also work. Or it could go to another fork in the road and do none of that at all. There is literally no work to be done in this inner loop over here. That is something called short circuit. So literally the electrons will never go into the inverter. So my inverter is always receiving a low. That's why when I'm running my simulation, no matter what I do with the switch, it's a low. And it outputs a high and lights up my LED. But the worst thing about it, this kind of setup is absolutely guaranteed to fry your battery, because there is no work to be done between positive end of the battery and negative end of the battery. But I still like this idea. I still want this to go, I still want this to be, I still think this is going to work. But maybe, just maybe, I need to add some work and in between my positive end of the battery, my switch, and my ground. And the best way to do that is just to add a resistor. So I'm going to grab another 330 and I'm going to place it in there. So here we go. All right. So now, when I'm going to run my simulation, when my switch is closed, my LED is off, and when my switch is open, my LED is on. So this kind of setup is called a pull-down resistor, because it pulls down the high value all the way to the ground, to low, or undefined value. All right. But turns out there is also another way to do this. And that would be to use another switch. So here's my circuit again. So if instead of this switch, I would use a switch that's called SPDT, and that is a switch with 2 terminals, I would be able to avoid this whole thing with pull-down resistor and just connect it directly to the ground. I'll be literally toggling between ground and high. So here's the SPDT switch, and you can see that it has one end over here and two ends on this side. So I'm going to connect the first one to the battery. The second one I'm going to connect all the way to the ground. This one I'm going to connect over here. And for this switch, I'm going to change the key, and it's not going to be space, it's going to be A. So this time, when I'm sending it a signal from the ground, the inverter inverts the signal and gives me a high. And when I'm sending the signal from the battery, the inverter inverts the signal and gives me a low, and the LED is off. Now, one thing that is not helping us build a tripwire in this particular case, this particular switch looks like a broken wire. And this one really doesn't. So this is a true circuit for the tripwire, and this one is more of a simulation circuit, because you have to use the pull down resistor over here to get that working. But it is useful to know about the existence of this switch, and we're going to use that switch a lot in this class.